for giving me the opportunity to give the lectures. So my plan is as follows. In the first lecture, I'll state the motivations for introducing exact digit categories. And then I'll define the category of three-term homotopy complexes, which is a key ingredient in defining exact digit categories. And in the second lecture, I will define the notion of exact digit category, and then show the embedding theorem. And I will end with several examples and illustrate our theory of exact digit category. So let's start. Let's start with our motivations. There are two classes of categories that we are interested in. First is Ealing-Woods-Higgs category H, which is associated with an S-quiver with potential, and it is an extension-closed subcategory of the relative cluster category, and this is a triangulated category. Okay, the second class is hypogeneous category of cohomolcular digit modules, and it is extension closed subcategory of perfectly valued derived category of a certain digit algebra. Okay, both classes of examples are extension closed subcategories of algebraic triangulated categories. So for this notion, see for Xiaofa Chen's lecture. And here, these relative cluster categories and the perfect valued derived categories are both algebraic. And so these two categories, X category and the category of cohomolcular digit modules, are in the framework of X triangular categories in the sense of Nakaoka and Pauli, and they are moreover Frobenius. And our aim is to understand this class of examples. So before going on, let me give the definition of algebraic X triangular categories. So by definition, C is an X triangular category if it is equivalent as an X triangular category to the H0 of an exact digit category, which is to be defined later. And we remark that this digit category A can be taken to be connective. So we simply truncate the exact digit category to get a connective one, and without changing the H0 of the exact digit category. And this X triangular structure, okay? And it can be shown that it is equivalent to the following two statements. Yes, the first statement is that the X triangular category is equivalent to a full extension closed subcategory of algebraic triangular category T. So here we can go back to our two classes of examples. So they both are extension closed subcategory of algebraic triangular categories. Okay. So by this statement, the Higgs category and the category of cohomolcular digit modules, they are both algebraic X triangular categories. And the second statement is the X triangular category is equivalent to an ideal quotient. This is an ideal quotient of a equivalent exact category by a full subcategory of projective injective objects. So So yesterday, Professor Nakaoka has given a recap on X-triangle category. So let me give a quick review. So we recall that an X-triangle category consists of a triple additive category C and a bimodule over C. So it's a biadditive bifunctor from 0 times C to the category of abelian groups. And this bifunctor is aimed to parameterize conflations in C. And S is a correspondence that sends elements in this abelian group. So it sends each element in the abelian group to an equivalence class of conflation in C. So recall that is equivalent. Two conflations are equivalent whenever there is such a diagram. Okay. So here, when we have an X-triangle category and we want to define an exact category, DG category, which enhances the X-triangle category C, we need to define this bifunctor in terms of the DG category. So we need a class of conflations. And our aim in the first lecture is to define the category of three-term homotopy complexes over A, where the required conflations will live in this category. And we will give an alternative definition using the homotopy theory of DG categories. Okay. So a quick remark is that here the first model, the category of three-term homotopy complexes over A, uses A infinity functors. So and it is more rigid to work with this category, and is suitable for diagram chasing when we want to prove some diagram lemma with DG categories. And but the second model, which uses homotopy theory of DG categories, has its own disadvantages. It is more, it uses certain bimodules, so-called quasi-functors. And its advantage is that it's more suitable for categorical arguments. So I'll explain this later. Okay, so let's start the definition of three-term homotopy complexes. Okay, so we need to we define this using infinity functors. So we need we need to define such a G category B. So throughout we'll fix a commutative ring, and our DG categories will be over K linear over will be linear over K. And our category B is the path category given by the quiver-Width relation. So here we have three vertices, 0, 1, and 2 arrows. And the composition of these two arrows is 0. Okay. Now the three-term homotopy complexes over A is defined to be the H0 of DG category. Okay, it is the DG category of strictly unitary A infinity functors. For this notion, we can see Bernhard Keller's lecture, and it starts from our DG category B to the DG category A, and it's different from the DG factor category from B to A, and it's totally different. We'll see this in a moment. So Professor Keller has defined n-infinity functors, but I think he didn't define strictly unitary. So let me give the definition. So first, we need our n-infinity category to be strictly unitary. So what's the meaning? So for each object A in the n-infinity category, yes, we have an identity map, which is from A to A, and is of degree 0, such that the differential is 0, and its composition with any map is that map, so composable with it. So G will start with A and anything another object, and F will start from some object to A. It's composable here, and moreover, the higher multiplications mi will be acting on a family of morphisms will be 0 when this I is greater or equal to 3, and at least one of the morphisms is identity of some object A for some A in A. So in particular, DG categories are strictly unitary. Here we can check this. For example, is higher multiplications will be 0, so this is satisfied. And because DG categories is defined so that is associative, the multiplication is associative, so this is also satisfied. And yeah, the identity differential is 0. It's also by definition. So here our DG category B and A are both strictly unitary. Now an A-infinity functor, yeah, Professor Keller leaves it as an exercise. Here I give the definition. So an A-infinity functor between A-infinity categories is given by the following data. So first we have a map between the class of objects, and secondly, for each n greater or equal to 1, we have a map of complexes. Yeah. For each sequence of objects B0, B1 to Bn, we have such a map between complexes. On the right-hand side is A from FB0 to FBn. This should be n. Yes. And this family of morphisms satisfy this equation. Yes, it seems it's complicated here, but for our purpose, in our case, our DG category B is very simple. We can see this. For example, the differential of any error is 0, and the composition of any and trivial morphisms is 0. So yes, when we check F2, when n equals 2, and here J plus K plus L equals 2. And we'll see that this K must be 2. Yes. And here, let me see. Write it. We have F. We have B from object 0 to 1 to 2. Our sequence of objects B0, B1, and B2 is 0 1 and 2. Okay, our F2 is this. And whenever there is an M1, then it vanishes. Yes. So this K is either 2, so that this becomes a composition, but the composition will be 0. Yeah, it vanishes. Okay, or this is just does not exist. So we find that we have F2 and then G, F. And then here L equals 1 and K equals 0. So we have a sign here, and it equals the right-hand side. And on the right-hand side, we have we can only apply M2 and F1 times F1 to GF. Okay. So now this becomes our diagram here. So at the level of F1, we assign to each morphism each arrow in the digit category B, a morphism F. Yeah, there are two morphisms F and J, and to the pair G and F, we assign a morphism in A. And we assign morphism H, and this Fn has degrees. So here H is of degree -1, and we ask that this is the differential of G and F. G composed with F. Yes. Yes. So here the A infinity functor is strictly unital when it preserves the identity, and whenever this for I greater than 1, and any one of these maps is identity, then this vanishes. So this will simplify our computation in this equation. So we summarize it. Concerning our category of strictly unital infinite functors, the objects are given by such diagrams. Yes, we have for each object in B, we have corresponding objects in A, and for arrows for these two arrows, we have the corresponding arrows, and for that pair, for the pair of these arrows, we have a degree -1 map, and this equation means that the differential of this map is the negative of the composition of these two. So and its morphisms, its morphisms, because here is H0 of a DG category. So the morphisms will be homotopy equivalence classes of certain morphisms. And here the morphisms are given by 6 tuples. So if we have 2 objects here in this category, then these morphisms are given by homotopy equivalence class of such morphisms, H1, H0, H1, H2, and S1, S2, and T. And here, the morphism H are of degree 0, morphism S are of degree -1, and morphism T are of degree -2. And the differential of H is 0. And here, in the homotopy category, we expect this to be commutative, and this S measures is the homotopy between the difference of the composition of these two morphisms and the composition of these two morphisms. And similarly, S2 is a homotopy between these two compositions, and T is the homotopy between two-step composable morphisms from X to Z prime. So here you can go from X to Z prime in 2 steps. There are only 4 ways. Here this is one way, and here this is one way, and this is another way, and this is another way. And the differential of T is a linear composition of this. It has certain signs according to how they go. Okay. So we also have compositions at the level of H is just the composition in the DG category, and but it will become complicated for S and T, the composition of S and T. And a special case is when the DG category A is concentrated in degree 0. Then this three-term homotopy complexes over A will be just a 4 subcategory of the category of complexes over A. So it consists of 3 terms. Yeah. For example, we ask this to be the 4 subcategory of 3 terms concentrated in degree 0, 1, and 2. Now let's introduce.
Sorry, here you mean it is full subcategory. So the morphism space are the same, you mean. But here the morphism space are much more complicated.
Yeah, but it is because our category is concentrated in degree 0.
Okay.
So maybe I can examine this. So when it's concentrated in degree 0, our H will vanish. We don't have -1 morphism. So these two compose to 0. So this is a complex. And we don't have S. So this will commute. And these two will commute.
Okay.
Yeah, because we don't have S. Yes, we don't have these maps.
Yeah. So when A is a DG category, then this is this a subcategory of CA?
No.
Okay.
No.
Okay. Thank you.
Okay. Now let's fix some notations. So let M be a complex, a cochain complex of K modules. We denote the soft truncation of N by this complex. So for degree less or equal to -1, we keep the original terms in N. And in degree 0, we take the kernel of the differential D0. And for morphism of complexes of K modules, we want to define its homotopy kernel. So in the DG category of complexes of K modules, so the homotopy kernel of G will be the universal 3-term homotopy complexes in the DG category of complexes of K modules. So it will be this object here. So its universal property means that for each homotopy 3-term complexes of this form, where the last 2 terms are given by the morphism G, and then there exists a unique map from this object to the homotopy kernel, such that the corresponding diagrams commutes. So here it commutes, and here it commutes. Okay, explicitly we can write this homotopy kernel as follows. So it's it equals the shift inverse of the cone of this morphism G. So as a graded K module, is equivalent. It equals the sum of phi and the shift inverse of W, and the map F will be the projection to the first component, and the morphism H will be the projection onto the second component. So it's degree -1, and we can check that differential of H is the manners of G and F. And the universal properties can be checked easily. Yeah, this map will be given by these two components. Yeah. U into the sum of these two. And we can check that this is a morphism of complexes.
Sorry, is the homotopy kernel a homotopy limit in some category?
Yes, we can define it using homotopy theory of DG categories.
Oh, okay, I see.
But yeah, we have homotopy kernel, and then we have homotopy kernel in the DG category of complexes, and we can define it in an arbitrary DG category A. So we consider a three-term homotopy complex over A, this. So F and G are of degree 0 are closed morphisms of degree 0. Suppose so the differential of both morphisms are 0, and the differential of H is the manners of the composition of these two morphisms, and we can apply a DG functor for each object A in A. We apply this DG functor, then we get a corresponding diagram in the category of complexes, in the DG category of complexes of K modules. And then we can we have this universal property. So we have a unique map from this object here to the homotopy kernel of this morphism. Yes, given by the universal property. Okay, and now this three-term homotopy complex is homotopy left exact when the truncation tau less or equal to 0 of this unique map is a quasi-isomorphism of complexes for any A in the DG category A. So so we leave it as an exercise to translate this quasi-isomorphism into a diagram chasing style. And dually, we can define homotopy right exact sequences over A. So in this case, we apply the contravariant DG functor, and then we get another diagram of complexes, and we can define it in the same way. Okay, and this sequence is a homotopy short exact when it is both homotopy left exact and homotopy right exact. So maybe let me give an example. So when A is concentrated in degree 0, then homotopy left exact sequences is nothing but left exact sequences. Yeah, because we have explained that when it is concentrated in degree 0, we don't have homotopies. So this will become a complex, because the composition of F and G is the differential of H. Okay, and for the same reason, because it's concentrated in degree 0, yes, and here when we apply the the home functor to this diagram, and to this diagram, and this here. This is this will be a triangle. Will give a triangle in the derived category of K modules. So if we take the homologies, we'll get a long exact sequence. And so, and now the negative homologies of this home complex, which is concentrated degree 0, will vanish. So we get that it is homotopy left exact if and only if this is exact of K modules. So this means that this complex in the additive category A, concentrated in degree 0, is left exact. Yeah, because we have this. Okay. And the second example is for in each DG category A, the graded split short exact sequence will give rise to homotopy short exact sequence. And for this notion, you can see Xiaofa Chen's lectures. So it's given by 3 objects in A, in the DG category, and which is a short exact sequence, and it splits in the graded category. So the composition of these two is identity. Composition of these two is identity, and yeah, the sum of these two is identity. Yeah, composition of this is 0. Composition of these two is 0. And the reason is that this such graded split short exact sequence will give rise to a quasi-isomorphism of DGA modules. So we apply the Unida DG functor, and then we'll get a morphism from A, the representable module by A to the cone of the representable morphism by P, given by this morphism. And this is a quasi-isomorphism. So this is a stronger condition than this one. This one is just in the truncation part, but this is on the whole part. Okay, so this will give rise to a homotopy exact sequence. Yeah, I, P, and 0 homotopy. Okay, next we give an alternative definition of this three-term homotopy complex over A, and the corresponding notion of homotopy left exact sequence and homotopy right exact sequence. So for this, we need to introduce several notions in the homotopy theory of DG categories. First, we have the category of small DG categories. So its objects are small DG categories. And these morphisms are DG functors. Okay. And this together with quasi-equivalences will have a model structure, the so-called Dwyer-Kahn model structure. So we can form its homotopy category. Yeah, it is still a category, not a large category. And we denote this by HQE. And in our lecture, our morphisms between DG categories will be morphisms in this category. And the derived tensor product of DG categories, we denote by this, is defined by this tensor product of DG categories. So B derived tensor product of A is B tensor cofactorant resolution of the DG category A. And this tensor product will define a monoidal structure on this category HQE. And for a pair of DG categories, we denote this category rep from B to A to be the full subcategory of BA bimodules. So it's a left B module, right A module, and such that when we restrict to each object B in the DG category B, yes, we get a DGA module, and we ask that this DGA module is quasi-representable. So it's quasi-isomorphic to a representable DGA module. And we can think of this category as the category of representations up to homotopy from B to A. And accordingly, we have the DG enhancement of this category. Yeah, because this is the category, the full subcategory of derived category. So we have the canonical DG enhancement of this category. We simply add a DG here. And for DG category A, we denote by pre-triangular A, the pre-triangular H of A. So it's universal from A to a pre-triangular DG category. And its H0 will be denoted by tri A. Okay. So as an example, when A is an additive category, so it's concentrated in degree 0, then its pre-triangular H will simply be the bounded complexes over A, the DG category of bounded complexes over A. And its H0 will simply be the bounded homotopy complexes over A. Okay. Now the tensor product here, the above defined tensor product, will define we have said is defined a monoidal structure, but it is a theorem of tone, back-tone tone, that this monoidal structure is closed. So it has an internal home. Its internal home is given by this rep DG. Okay. Then we'll need the following theorem. Due to canonical and Oknagi and Stellari, and is claimed by Konsovich, but the proof is due to these 3 authors. And it's that we have a canonical isomorphism of bifunctors between the strictly unital infinity functors and the rep DG that is from HQE and a full subcategory of HQE op. Here it is a full subcategory, consists of DG categories with cofabrant home complexes. So it has this is just for technical reason, but for the DG categories that we are considering, it will all be cofabrant. Here, let me go back to the DG category we start with. Yes, here, this DG category will have cofabrant home complexes. Yes. So, because our category of three-term homotopy complexes is defined by H0 of this, and we have such isomorphism of bifunctors, so we can use RepDG to define this category of three-term homotopy complexes. So let me first introduce the category B prime. It is a resolution of this category. So here is the DG Pascal category of the graded quiver, consists of 3 objects and 2 morphisms of degree 0 and the morphism of degree -1, and these two are a closed morphism, and the differential of this morphism is the minus of this composition. So it's a cofavariant DG category, and is quasi-equivalent to the past K category that we begin with, 2 errors and vanishing composition. So our three-term homotopy complexes, a category of three-term homotopy complexes over A will be equivalent to this category of representations up to homotopy from this DG category B prime, so DG category A. Okay, we can further embed this DG category into this DG category is the last category of this quiver. So we have these 4 errors such that the composite of these two equals the composition of these two. Okay. So up to isomorphisms, objects in the rep from K squared to A will be given by a square of DGA modules, such that each xi is quasi-representable DGA module. Okay. Okay. And then let's go back here. On the left-hand side, this category can be identified with a 4 subcategory of this category, where this object is acyclic. And I think it's an easy exercise to show this fact. And so we can interpret the previous notions of homotopy left exact, homotopy right exact, and homotopy exact sequences inside this category rep from K squared to A. Okay, for example, we define this square to be homotopy Cartesian. So if the canonical map from x0 to the shift inverse of the mapping cone of these two, we have a morphism from the sum of x1 and x2 to x3 given by these two components. And because this is the composition of these two equals the composition of these two, we have a canonical map from x0 to the shift inverse of the cone of this map. So it's this map. And it is homotopy Cartesian square if and only if this is a quasi-isomorphism. It induces a quasi-isomorphism between these two complexes. Yes. And we can also define homotopy co-Cartesian square by first identifying objects in three-term homotopy complexes with square of DGA modules, and then interpret the conditions here to there. Yes. Yes. So let me give a remark. I think this is important. So for cospan in the DG category A, so our B, C, D are objects in A, not A modules. They are objects in A, and such that these two morphisms are closed of degree 0. Then we define its homotopy pullback to be a diagram in A. It's such a diagram. So its homotopy pullback such that if this sequence is homotopy left exact, because H is a homotopy between the composite of these two. So this will define a three-term homotopy complex over A. But if we define homotopy pullbacks in terms of this category. In terms of this category, rep from k squared to a, we will have to have an isomorphism. So if we have a corresponding diagram in the category of DGA modules, yes, we simply apply the union-type DG functor. Then is homotopy pullback is a diagram. This commutes, which is homotopy Cartesian. Yeah, above we have defined homotopy Cartesian square. So it's homotopy Cartesian, but its restriction to this cospan is isomorphic to S prime. It's not equal to S prime. So this will cause some problems when we are doing proving some diagram lemma. Yes. So I think I'll stop my first lecture here.
Thank you very much for your nice lecture. Now it's time for the question. Please feel free to unmute yourself or write in the chat. I think there is a question in the chat. Can you see?
Here, you mean this? If we do not truncate it, I think it will be the homotopy kernel. Yeah, I'm not sure here.
Are there any further questions or comments? So it seems that there is no more questions. So let's thank Xiaofa again. Thank you very much. We will be back in around 9 minutes.